In this video, we're going to prove a result that's a frequent question on algebra qualifying exams. If you can compute the tensor product of any two R modules, this is a really good one to know. Let's say A and B are positive integers, with D being their GCD. Then the tensor product of the two finite cyclic groups, Z mod AZ and Z mod BZ, is isomorphic to Z mod DZ. Okay? Z mod AZ is a Z module, Z mod BZ is a Z module. What is a Z module? It's just an abelian group. This is isomorphic as a Z module to the finite cyclic group Z mod DZ. In particular, this tensor product is 0 if and only if the GCD of A and B is 1. If D is 1, we're getting Z mod Z, the trivial group. Okay, so how are we going to prove this? We have a spanning set for the finite cyclic group Z mod AZ. 1 is a spanning set. We have a spanning set 1 for Z mod BZ. And this result that we proved earlier, that if you have a spanning set for M and a spanning set for N, you get a spanning set for M tensor N, shows that this single elementary tensor, 1 tensor 1, spans the tensor product Z mod AZ tensor Z mod BZ. So we know that this is a cyclic group, this tensor product. We just have to determine the size of this group. And we're going to show that the size is equal to exactly D. We're going to do that in two pieces. First, we're going to show that the order of 1 tensor 1 divides D. This is the easier piece, which is going to say that the size of this thing, okay, divides D. Then we're going to show that, in fact, it's equal to D by showing that it's greater than or equal to D, by showing that there is a surjective Z-linear map, F, from this tensor product to Z mod DZ. How are we going to come up with a linear map from a tensor product to somewhere? Well, what did we say earlier in this lecture? We're going to back up and we're going to define a bilinear map from Z mod AZ cross Z mod BZ. All right, let's get to it. Let's prove this first part, that the order of 1 tensor 1 divides D. Well, we know that A times 1 tensor 1 is the same as A tensor 1, which is 0 tensor 1, which is 0. We also know that B times 1 tensor 1 is the same as 1 tensor B, which is 1 tensor 0, which is 0. So what are we seeing? The order of 1 tensor 1 divides A, and the order of 1 tensor 1 divides B. So the order is a divisor of A and a divisor of B. So it divides the greatest common divisor, D, of A and B. So I'll pause and erase, and then we'll talk about how to do this second part of the argument. Let's finish the proof of this computation of Z mod AZ tensor Z mod BZ by showing that this tensor product has size at least D, the greatest common divisor of A and B. So since D divides A and D divides B, we have reduction maps where you take an element in Z mod AZ and you say, what is it mod D? Similarly, Z mod BZ, what is it mod D? Because D divides A and D divides B, this map is actually well defined. We're going to consider the map B that takes an element in Z mod AZ cross Z mod BZ and outputs an element in Z mod DZ defined by taking X mod A, Y mod B to XY mod D. So what is this function doing? You reduce and multiply. So you look at X is an element in Z mod AZ that gives you an element in Z mod DZ. Y is an element in Z mod BZ that gives you an element in Z mod DZ, and then you multiply them together. This is one of the challenging pieces of this argument, is you have to remember what this map is. So this map is going to be the key to the whole thing. So I encourage you to really think about this example. This map is Z bilinear. That is something that you should check. It's not obvious, but you can check just by using things about multiplication and addition and Z mod NZ, this really is a bilinear map. Now, the universal mapping property of the tensor product says that given this bilinear map from Z mod AZ cross Z mod BZ to Z mod DZ, there exists a unique Z linear map from the tensor product to Z mod DZ that makes the following diagram commute. You start at the direct product, you apply B, you go down to Z mod DZ. Or you go around the other way. You take the tensor of a pair A comma B, then you apply this unique Z linear map F. So what does that really mean? That means you apply F to X tensor Y, and you get XY in Z mod DZ. All right, so what is true about this map? Well, if you just take Y equals 1, F of X tensor 1 is X. So X is an element in Z mod AZ, and you get X mod D. You get the reduction in Z mod DZ. So in particular, this already is enough to show that F is surjective. And once we know that there's a surjective map from this tensor product to Z mod DZ, well, that means that there's at least D elements in this tensor product. So this tensor product has size at least D, and we're done because we already showed that the tensor product is a cyclic group and that its order had size dividing D. So what's the big thing that we did here is we wanted to show that this tensor product had size at least D. I mean, we had to show that this tensor product was not 0. Well, it is 0 when D is 1. But what did we do is we wanted a surjective map from our tensor product to Z mod DZ. And how did we come up with it? We had to back up and define a bilinear map out of the direct product of M cross N. So where do linear maps from the tensor product to somewhere, in this case, Z mod DZ, come from? They come from bilinear maps from M cross N to that same place.